Dear students, today we will start from the first lecture of quantum mechanics, paper 3, according to Punjab University syllabus. Chapter 1 जिसका नाम है ब्रेकडाउन ऑफ क्लासिकल कॉन्सेप्ट्स एंड ओल्ड क्वांटम थ्योरी। इसमें हम दो टॉपिक्स कवर करेंगे, एक इंट्रोडक्शन टू क्लासिकल फिजिक्स और दूसरा व्हाट इज द ओरिजिन ऑफ क्वांटम मैकेनिक्स। Now we will start from the introduction to the classical physics. Quantum mechanics basically is the theory about nuclear and atomic physics, and this quantum physics is developed by classical physics, particularly two branches. One is the Newtonian mechanics and second is the Maxwell's electromagnetic theory. First, we review Newtonian mechanics briefly. As we know that matter is regarded as made up of particles and they are interacting according to mutually interacting forces, and these interactions and forces can be explained by Newton laws of motions, and one famous law is the second law of motion, which is the product of mass and acceleration, and we use this law with law of gravity to explain the motion of objects and in their interaction. So this theory is very successful in explaining the motion of planets, and also it describes the motion of electrically neutral microscopic particles. So as we know that matter in terms of particle has definite mass, and having mass, their motion of free particle is defined in terms of energy and momentum. In classical physics, second theory is the Maxwell's electromagnetic theory, as classical physics is also concerned with electric and magnetic phenomena, and these electric and magnetic phenomena are best described by electric field E and magnetic field H, and these electric and magnetic fields are related to the current and the charge densities respectively. From this we can conclude that in free space both electric and magnetic fields satisfy the equation number 1 and equation number 2. Solution of previous two equations gives the electric field E and the magnetic field H, and these E and H propagate through the space as a wave, and this wave travel with the speed equal to the speed of light, that is c. So spectrum of radiation which starts from the very long wavelength, that is from radio waves, and end at the very short wavelength, that is at X-rays and gamma rays. These all electromagnetic radiations are explained by the electromagnetic wave theory, and which is given by Maxwell and Maxwell equations, and the traveling waves equation can be written as psi is equal to a e raised to power iota k of x minus omega t. In the traveling wave equation, k is equal to 2 pi over lambda is known as angular wave number or propagation constant, and omega is known as angular frequency, which is equal to 2 pi nu. So C can be written as C is equal to omega over k, and using the value of omega and k we get a relation between C, V and lambda, that is the speed of wave. So Newtonian mechanics and electromagnetism both are coupled in the form of Florence force, which states that a particle of charge E moving in an electric and magnetic field with velocity v is subjected to the force which is given by F is equal to electric force plus magnetic force. Both forces are present and net force is called Lorentz force. From classical point of view, matter consisting of point charges and radiation consisting of waves would have provided the framework for the fundamental description of physical phenomena. So for point particles, electrons and protons, as we know that they carry mass and electric charge, and they are interacting by the electromagnetic and gravitational forces. These point charges and their motion are explained before the discovery of photon by the classical physics. Now we start with the origin of quantum mechanics. Few physical ideas and experimental facts gave rise to the birth of quantum mechanics. This birth of quantum mechanics is due to the failure of classical physics at the microscopic level. So at the end of the 19th century, there were two successful theories. One was the classical mechanics, other was the theory of electromagnetism with thermodynamics. So classical mechanics, as we know that it describes the dynamics of material objects, material bodies, and Maxwell theory gives rise to the phenomena of radiation and explain the phenomena of radiation. Matter and radiation were best described as particles and waves respectively. An interaction between matter and radiation was explained by Florence Force and by the thermodynamics. These two theories, classical physics theory and classical theory of electromagnetism along with thermodynamics, were successful and people believe that these are the ultimate description of the nature. And all known physical phenomena were explained on these theories in form of matter and radiation. So in the 20th century, classical physics encountered two major challenges. One is in the relativistic domain and other is the microscopic domain. First we consider the relativistic domain. In this domain, Einstein 1905 gave the theory of relativity, which shows that Newtonian mechanics ceases at very high speeds, means speed of light. Newtonian mechanics is not applicable on the dynamics of particles moving with the speed equal to the speed of light. The second domain in which the classical physics fails is the microscopic domain. So the dynamics of particles at microscopic level cannot be understood by classical physics. So classical physics ceases at microscopic level. So example of these phenomena include the black body radiation, photoelectric effect, atomic stability, and atomic spectroscopy. These cannot be explained by classical physics, so these should be explained by new mechanics known as quantum mechanics. For this purpose, the first breakthrough came in 1900 given by the Planck, and he introduced the concept of quantum of energy.